Bismillahirrahmanirrahim. I'm Dr. Muhammad Wasim, and in this lecture, we will study about the runoff calculations from the subject of hydrology and water management. After completing this lecture, you will be able to calculate the peak runoff by the rational method, and then we will study about the um, modified rational method, NRCS method, and then in the end, we will calculate the runoff hydrograph by the NRCS method. So what exactly is rational method? So we use the rational method to compute the peak runoff, which we will denote in this lecture with QP after falling a rainfall event. We know that when there is a rainfall event, there will be runoff. So this rational method is only about to calculate the peak runoff, and we are not interested in this rational method the peaks before the peak runoff and the peaks after the peak runoff. So we are only interested in the peak runoff of falling a rainfall event. And in this method, we do not make any attempt to estimate runoff before or after the peak, but simply we quantify the flow which is the greatest. So the rational formula for the peak runoff is QP is equal to AI. QP is peak runoff in CFS, A is drainage area in acres, I is the rainfall intensity in inches per hour. CFS is cubic feet per seconds. So if you want to take the peak runoff in cubic meter per second cubics, then the formula will be different. So in some of the books, you will see different formulas of rational method, but then you need to take care that the drainage area will be in some different units, the discharge will be in some different units. So they will place the conversion factor in the start of this formula. So there is nothing different in those formulas, just the units are different. So this rational method is based on a completely impervious drainage basin. Impervious means that all the rainfall is converted to runoff because there will be no losses. So later, a proportionality factor C called the runoff coefficient was added in the formula. Why it was added? To account for the infiltration into the ground and for the evapotranspiration losses. So the formula for the rational method was changed from QP is equal to AI to QP is equal to ACI, where C is the dimensionless runoff coefficient, and its values varies from 0 to 1. So if it is like fully impervious, then it will be 1, and if it is a fully pervious, then it will be 0. So like if the catchment is a paved, mainly consists of paved surfaces, then it will be more closer towards the 1 value, like 100%. And in some cases, let's say our concrete paved roads, it will be something 0.95 because they are not 100% impervious. So this is how you will determine the C values. C values you can find from the literature for different land use types. Yeah. So rational method, in this diagram, you can see the relationship of rainfall intensity to runoff for an impervious drainage basin according to the rational method. So here you can see in this diagram at the top, there is a rainfall intensity, and rainfall intensity is nearly equal to, not nearly, exactly equal to the time of concentration. So when the rainfall event is equal to the time of concentration, let's say it takes 10 minutes or 15 minutes from the remotest point, the runoff from the remotest point to reach at the point of analysis, right? And exactly at that time, when the runoff from the remotest point reach the point of analysis, rainfall stops. So this will be the point where you will observe the peak. Yes, so this is basically happening in this diagram, which is a relationship of rainfall intensity to runoff for an impervious drainage basin, right? So this is because in rational method, we have assumed that our catchment is impervious. So let's see the theory. The original reasoning expressed in the rational method is described as follows. Consider a drainage basin with area A that is rained on at a constant intensity I. So here we have a drainage area, right? And there is a rainfall event on a constant intensity, and our intensity is constant, and that intensity was constant for a period equal to the time of concentration. And then we will assume that no rain falls before or after the downpour of intensity I and duration time of concentration. So in simple words, our rainfall event was exactly equal to the time of concentration, right? And intensity was constant. There's nothing about the depth of rainfall. We are just saying that the intensity is constant and the duration of that constant intensity rainfall event was equal to the time of concentration, right? So then this is a relationship. So we move towards the next slide. Now, first point we have already discussed. Now, the second point from here. Now picture yourself at the point of analysis, watching the runoff falling by. So now I am standing at the point of analysis where all the water is coming from the catchment, and I'm watching the runoff flowing by. As soon as the rainfall starts, some runoff flows by. It's simple that as the rainfall will start, the runoff from the nearest points will be quickly reached to the point of analysis. This early runoff comes from rainfall that landed near the point of analysis. It's clear to us. As time goes by, runoff increases as raindrops from further away points reach the point of analysis. But even as these further raindrops arrive, the closing raindrops are still arriving because it's still raining. So finally, there will be a time which will be equal to the time of concentration. The remotest raindrops arrives at the point of analysis. And exactly at that moment, the rainfall stops. Then this makes the maximum runoff rate, right? Because the water from the remotest points reach to the point of analysis, and exactly at that point, the rainfall stops. And then when the rainfall stops, then the flow rate becomes declining immediately, and the water from the remotest point, when the rainfall stops, will take time equal to time of concentration to get out of that point of analysis. So then, finally, to quantify peak runoff, examine the figure 11-1, which we have shown already. The total runoff volume equals to the area under the graph of the runoff versus time. So the volume computed in cubic feet is half 2 into time of concentration into QP. So this is basically the diagram. So here we are multiplying the area with the discharge, peak discharge. So that will be equal to the volume. And why it is equal to the volume, we have already discussed in the last lecture. So 60 is for changing the time of concentration into seconds. So now we have the volume. But we need to remember that because the drainage basin is hypothetically completely impervious, as we have hypothetically assumed that our drainage basin is impervious, so the total runoff equals the total rainfall. Because as much as there will be rainfall, there will be equivalent amount of runoff. So the total rainfall is computed simply as the depth of rainfall times the area. Right? So the total rainfall is computed depth of rainfall multiplied with the area over which the rainfall occurred. So the depth of rainfall in feet is the rainfall intensity converted to feet per second times the duration converted to seconds. So we have the depth I divided by 12 to change it into the inches, and then 3600 to change it into the seconds, and then our time of concentration was 60 seconds. So it becomes I into time of concentration over 720. And the rainfall volume is equal to depth into area. So we have the depth and we have the area. Area here, as I told you in the formula, that we use the area in acres. So in acres, we have 43560 feet square. So we'll get the volume as 60.5 ITC into A. And then we will finally equate both of these volumes. The volume we have estimated in the last slide and the volume estimated here, which is 60.5 ITC into it. So we will compare both of these volumes, and then we find the QP as 1.0083 AI, which is nearly equal to, or we can consider it as equal to, QP is equal to AI. But this is for the impervious catchments, not for the pervious catchments. Because here we haven't estimated or we haven't accounted any losses. But then we have already explained you that to account for the losses, the runoff coefficient C was introduced. So C values, its value was from 0 to 1. So here in literature, you can see different C values for different surface types. If it is impervious pavement roofs, then we go from 0.75 to 0.95. For lawns, it is 0.05 to 0.35. For unimproved wood or brushes, then it goes from 0.10 to 0.3. And then we have typical design values. So if you see in the note, these values of C are typical for lower intensity storms up to 25 years return period. Higher values are appropriate for large design storms. And you can see the appendix C-1 in Johnny Gribben book of hydrology and hydraulic design. So there you will find the appendix C1, and you can find the values for different storms of different return periods. To account for infiltration and evapotranspiration of runoff with proportionality constant, C was added to the equation, and values of C I have already explained, and these are in table 11-1, which we have already discussed. So now we know that up to this point, that the rational method is only used to determine the peak flow rates. And we are not interested, and we do not try to estimate the peaks before the maximum peak and after the maximum peak. And then the next thing which we studied was that the catchment was, or the drainage basin was, hypothetically completely impervious, and our QP was area into intensity, AR dot I. And then we introduced the runoff coefficient C to account for the losses for infiltration and evapotranspiration, and it has different values. Its value range from 0 to 1. Then we have found the volume for both the cases, and we equate both these volumes and prove the formula QP is equal to AI. And in this formula, you need to remember that your area, your area is in acres, and your QP is in CFS, and your intensity is in inches per hour units. So then, here we have find the formula. So next is the fact that rain is falling on the catchment area 4 and after the time of concentration does not change the value of QP. The only effect is to change the shape of the hydrograph, shape of the graph of runoff or hydrograph versus time, or shape of the hydrograph. So keep in mind that actual rainfall covers a period of several hours. It is really like sometimes interesting that you will assume that if the rainfall is more than the time of concentration, yes, as a student, I think that if the rainfall is more than the time of concentration, then why the peak is at the time of concentration? This could be a question. So keep in mind that the actual rainfall covers a period of several hours. We can choose to focus on the most intense portion of the rainfall event, having a duration equal to the time of concentration. Any other duration, whether it is the rainfall event is more than time of concentration or less than time of concentration, will result in a smaller value of QP, peak discharge. If we choose a duration less than time of concentration, what will happen? The intensity would be greater, but we would not include runoff from the entire basin. Because it will take more time from the remotest point to reach the point of analysis, and before even that event to come, the rainfall event is already stopped. So you will not see the peak as high as equal to the rainfall event equal to time of concentration. So now let's say in second case, if we choose a duration greater than time of concentration, so we know that if a duration is greater than time of concentration, the intensity would be less. So thus mathematically the amount of rainfall will be reduced. So I know there could be confusions. It's difficult, sometimes complicated to understand these terminologies. We will solve our problem, but at this point, I repeat, let's say we get the peak when the rainfall event is equal to the time of concentration. Let's say student X asked me why, when the rainfall event's duration is less than time of concentration, why the peak is lower. Because let's say the rainfall droplet or runoff takes 30 minutes from the remotest point to reach the point of analysis. And now your rainfall was, so time of concentration is 30 minutes, but your rainfall event you have choose is for 15 minutes. So what will happen? The rainfall happens for 15 minutes over the catchment. But from the remotest point, it will take 30 minutes to reach the point of analysis. So when the time of rainfall event's time is less than the time of concentration, you will not observe the peak discharge as equal to the peak when it is exactly equal to the time of concentration. Because when the water from the remotest point will reach, the already peak has gone. Because the rainfall event was for lesser duration than the time of concentration. And the rainfall after 15 minutes stopped, and the water which was nearest point to the point of analysis has already passed on. When the water from remotest point came to the point of analysis, the nearest point's water has already gone, and the rainfall event was stopped 15 minutes already. So the hydrograph was already in the downfall side, was already declining. So this has happened. So now let's say when the time of concentration is more, if the rainfall event is more than the time of concentration, then we knew that from intensity, duration, and frequency curves, when the duration increases, the intensity decreases. So mathematically, the peak will be reduced. So let's move towards a rational method problem, so it will clear much of the things. So here we have a case, compute the peak runoff QP for 25-year storm using rational method. So 25-year storm meaning that it happens once in a 25 years. And we have to find the QP. And the region is located in Pennsylvania, having the following parameters. Area is 24 acres. And then we know that second step is the given data, the time of concentration we have to find. Then they are saying that overland flow, the land use type is average gross surface, length is 100 feet, slope is 2%. Then there is a shallow concentrated flow, length is 750 feet, slope is 4%. Then there is a stream flow, and we have a length of 100 feet and slope 0.4%. And the average cross section is given an n value, which is the Manning roughness coefficient is 0.032. And then we have also got some runoff coefficients. C values for impervious, it is 0.5 acres. Grass is 11.5 acres. Wooded is 12 acres. And C values for all these different land use types is given. So as we have already discussed, you can see in impervious, our C is more towards the value of 1. And for wooded, it is more towards the value of 0. So this is basically the given data. So first step, we have to find the time of concentration. We know that for overland flow, we find the time of concentration from the nomograph. This we have discussed already in the previous lecture of chapter 1, which was basically the fundamental of hydrology. So to compute the QP, the values of A and I and C must be determined. So in this case, A is known to be 24 acres. To find the intensity I, we must find first the time of concentration. So the time for overland flow T1 is found from the nomograph appendix C2. So for this is the line which is shown here is just for different land use type. So we already have discussed how to read the nomograph for different land use types. So in our case, it is 100 feet, slope is 2%, and the land use is average grass surface. So you just need to go to 100 feet here, somewhere here. Then you have to direct straight come to the average grass surface, and you will extend this line up to the pivot line. And then you have the percent slope, which was, I think, 2%. You have to again from this point, 100 average grass, and you extend this line to pivot line, and then, and then you go to 2% of slope and come here in a straight line. So it will be something like 12 or 12 and a half. If you have a ruler, then you can clearly calculate the values. So in this case, I have explained you how to study the nomograph. So in this case, for overland flow for the given data, the time of concentration was 12.5 minutes. So the time of shallow concentrated flow T2 is found from figure 10-9 using the surface as unpaved. I think these curves I have already explained you in my previous lecture that how to read these values. So you can just see this figure number 10-9 and go to the unpaved surface and find the velocity from that figure. This is already provided in the previous lecture of fundamental of hydrology. So V is 3.2 feet per second, and then the time is distance over velocity, and in our case we will get the time T2 for shallow concentrated flow as 3.9. Then our average cross section was given here. We have found the area wetted perimeter, and then from area we got as 27 feet square. And wetted perimeter as 14.5 feet. And then we can find the hydraulic radius, which is R is equal to area over wetted perimeter. So it came out to be 18.6 feet. Next, we find the B. We have to find the velocity from Manning's equation, which is 1.49 over n on raised to power 2 by 3, S naught raised to power 1 by 2, right? So we have all these values. We have the slope, we have the hydraulic radius, we know the n, and then we find the velocity, which is 4.45 feet per second. And then we find the third time of concentration for the stream flow, which is equal to 3.7 minutes. And then we found the total time of concentration by adding all these 3 times of concentration for different type of flows. Initially was sheet flow or whirlwind flow, and then the shallow concentrated flow, and then the stream flow. So our total time of concentration is 20.1 minutes. So the time of concentration is 20.1 minutes. So the rainfall intensity is found by using the IDF curves for Pennsylvania region, shown in this appendix C3, which you can see on this slide, using the 25-year storms, and then you can find the intensity here. So we have, I think this is the 25-year storm curve. We have time of concentration, let's say 20.1. Just consider it more or less to 20, and then you can find it is somewhere. "25-year storm." Yes. So it is somewhere, this is the line, sorry, because this are more or less difficult to distinguish. So this is the line of 25-year storm. So if I go somewhere here, 20 minutes, and come here, so it is somewhere at 20.1. So this is basically 20.1, and here you can find the value, which is 2, 3, and 3.4 inches. This is basically a log graph, right? Maybe you have studied in your college that how to read the log graph. But yes, this is confusing to find this 1-year storm, 2-year storm, 5-year storm. In this case, this is the curve for the 25-year storms. It could have been better if these in different colors. So we get the intensity, and then what we do, we need to find the composite C value. Here in the given data, these are runoff coefficients. We know that for impervious, which is 0.5 acres, our total area was 24 acres. If you add this 0.5, 11.5, and 12 acres, it is equal to the 24 acres. And then we have divided the 24 acres into impervious, which is 0.5 acre. Grass is 11.5, and wooded is 12 acres. Then we have the different C values for all these land uses. So what we did was we found a composite C value. So 0.5 into 0.9. So 0.5 was the area of impervious land, and C was the 0.9, plus 11.5 into 0.35. 11.5 was the area of the grass, and the 0.35 was the C value, and similarly 12 acres and 0.25. So what we did, we divided by the total number of acres, which was 24, and we found the composite C value. And finally, we can find the QP, which is ACI. A was 24 acres, C is 0.31, and I is 3.4. And then we found the QP in CFS, cubic feet per second, which was QP, peak discharges 25 CFS for rainfall of intensity. We got the intensity of 3.4 inch per hour, and then the time of concentration and the total time of concentration is 20.1 minutes. So this is how you find the peak discharge by using the operational method. So one more thing to clarify the stuff, I would like to read these slides because I think this will clear most of the doubts. So let's say it may seem curious that a rainfall duration exactly equal to the time of concentration results in the maximum possible runoff in the rational method. To understand why this is true, consider the following example. A 10-acre drainage area in New Jersey has a time of concentration of 30 minutes. 30 minutes for a 10-year storm. Which rainfall duration will produce the greatest peak 1 QP. So case 1, rainfall duration equals 20 minutes. So our case 1, the rainfall duration is less than the time of concentration. The case 2, the rainfall duration equals 40 minutes. So it is more than the time of concentration. And the number 3, rainfall duration equals 30 minutes. Right? So this is only about the rainfall duration. You need to keep in mind we are only discussing here the rainfall duration and we have the time of concentration. There is nothing about the depth of rainfall. The intensity will change when the duration will change. This thing you have to keep in mind, and those we will find from the intensity duration curves. Or as we are dealing with the New Jersey, so we'll have to go into the New Jersey appendix. So keep in mind that the overall rainfall event lasts many hours and we can choose any duration from the event we want. We have the privilege. The 3 graph shows the relationship between rainfall intensity and runoff for each of these 3 cases. For case 1, the rainfall intensity I is 4 inch per hour, shown on the IDF curve for New Jersey in Appendix C. You can just go to New Jersey Appendix C curve and then you can find the intensity, which is 4 inches per hour. But since the rainfall lasts only 20 minutes, when it stops, runoff from the upper portion of the watershed has not yet reached the point of analysis. So the water from the remotest point has not reached the point of analysis and rainfall event has been stopped. So what happens by that time, the upper runoff reaches the point of analysis, rainfall has already ceased. So there is no runoff from the lower portion to add to the upper runoff, and consequently total runoff is less than it would be if the rainfall continued for the entire time of the remotest runoff was traveling from the across the watershed, which was equal to the time of concentration. So QP is consequently is 32 CFS. So this is basically the case 1. So let's go to the calculation. So our volume is 4, intensity is 4 inch per hour, and then we change the hour into 60 minutes, and then we have time of concentration as the rainfall duration as 20 minutes, and then we have we change this into inch per hour to foot per inch, and then we have the area for acre, which is basically 43560 feet square per acre, and the total area is 10 acres, which is given here, the 10-acre drainage area. So we got the volume as 48440 cubic feet. And then we have found the volume as half of the 50 minutes, multiply 60 seconds over minute into QP, and then we got the, which is basically the way of finding the volume of this triangle, which is shown here for the case 1. Because this is for base is 50 minutes, and we are multiplying it with the QP, and then we finally comparing both of these volume as we did it for when we were like finding the formula of QP. So here the QP is 32.3 CFS. Let's say in case 2, I is 2.75 inch per hour. So here this intensity is changing. You need to keep in mind that the intensity is changing. Initially it was 4 inch per hour, and now it becomes 2.7 inch per hour, because for a storm of 10 years, if the duration changes, then the intensity changes from the intensity, duration, and frequency curves. So now the intensity becomes 2.75 inches per hour, which is more than the time required for the remotest runoff to reach the point of analysis. And here we get the QP as 28 CFS. How we calculated this? Volume is 2.75, intensity volume is being calculated as intensity is 2.75 inch per hour, and then we have 1 hour is 60 feet, and then we have 40 minutes of this rainfall duration, and we change this inch to feet, 1 feet, then 12 inches, and then the area is 10 acres, and we changing these 10 acres into feet square, 43560 feet square per acre, and then we got the volume as 66550 cubic feet. And then we are trying to find the area of this triangle. Then it is half into 10 plus 7, 10 minutes plus 70 minutes by 2. And then there is a conversion 60 seconds into 1 minute into QP. And then we compare both of these volumes and we find the QP as 27.7. Right? So we got the QP less than the first case. So even our rainfall event was for the larger duration than the time of concentration. So in the third case, which is time of concentration, is exactly equal to the rainfall event. So here the intensity changes to 3.3 inch per hour. So for this, we have just changed the we did the conversions as we are already doing. So hour we changed into minutes, and then we have a 30 minutes of rainfall duration. So 1 feet or 12 inch, and then again we changed our 10 acres into feet square. We got 59,895 cubic feet, and then we are finding the volume of this triangle. So base is 60 minutes, and this is a triangle, so we take the half, so and multiply it with the QP, and finally we got the QP as 33.3 CFS, which is basically the maximum peak when our rainfall is equal to the time of concentration. So hopefully this is now clear that when the rainfall event is equal to the time of concentration, we will get the maximum discharge. Hopefully you have understand this first part of the lecture of runoff calculation.